This is my second part of case study. I represent this now. It's the other parts of my problem and solutions. Total load at station 2 equal to 50 minus A equal to 50 minus 1.666 equal to 48.334 megawatt. This is the answer. Here, lesson 4, comparison between UC unit commitment and with economic load dispatch. Here is the comparison: unit commitment UC and economic load dispatch. Necessity of spinning reserve. Here is the answer. The spinning reserve is the amount of unused capacity in online energy assets which can compensate for power shortage or frequency drops within a given period of time. If the largest generator in the power system is stripped, the remaining generators should increase their output to recover the power shortage. So some generators in the power system are required to operate below their rated value to prepare for unexpected demand or contingencies. The more reserve is needed, the operating points of generators are further away from the rated value and thus are less efficient. Also, if the generator works under inefficient conditions, carbon dioxide and other emission will increase. Some system capacity has to be kept as spinning reserve: 1. To meet an unexpected increase in demand, and 2. ensure power supply in the event of any generating unit suffering a forced outage. 3. Derive the total expression for cost function for solving unit commitment when j equal to 1 to m. Here is the expression. The total expression is present here. State of cost consideration. Here is the state of cost consideration equations. Shutdown cost consideration. Similarly, if a plant is taken out of service during the scheduling period, it is necessary to consider the shutdown cost, and here is the expression. Priority list method. Here presents the priority list method, which is lesson 6. Here is the total method present here. Load frequency control. It is the parts of lesson 7. Load frequency control. Necessity of maintaining frequency constant. Load frequency control. Governor characteristics. It is lesson 8A, and here is the figure. Characteristics of typical governor to steady state of speed regulation in per unit. Here is the figure. Speed governor setting. And PF control. Here is the figure. ALFC loop, AVR loop, PF controller, turbine, generator, QV controller, comparator, frequency sensor, voltage sensor, It is the schematic diagram of PF controller and QV controller. And it is the figure speed governor system figure. This figure is present speed governor system. Speed governing system, here discuss about speed governing system. Then speed changer, power system security, lesson 11. And here is the application of long-term planning, operational planning and online operation. Here is the application of long-term planning, evaluation of generation capacity requirements, evaluation of interconnected system power exchange capability, evaluation of transmission system adequacy, operational planning application and online operation. Here is the total 11 lessons is represented my case study. And here is the security analysis. Security analysis is the determination of the security of the system based on a next contingency set. This involves verifying the existence and normality of the post contingency states. If all the post contingency states exist and are found to be normal, the state is secure. On other hand, the non-existence of even one of the post contingency states or emergency nature of an existing post contingency state indicates that the current state is insecure. Here is my total representations are present in my case study. Thank you all. Good day.